Okay, so now let's do exactly the same thing, but this time we're going to build a regression tree. Now, a regression tree is very, very similar to a classification tree. So again, we just put our dependent variable and then we put all our independent variables. So let's just run this now. Incredibly quick. Now we can actually do visualizations of our regression tree in a similar way to our actual classification tree. So let's look at this one here. Now notice that we actually have, it's kind of very similar to what we had before. Here we go. We have our yes and our no branches. We kind of actually branch either on categorical variables or kind of on subsets of continuous variables. So let's just have a look. These are the kind of the nodes of the tree at the bottom, and this indicates, you know, the risk of heart disease in the population. And let's just kind of go through a few branches of the tree. So let's just say that you have diabetes less than 0.11, so less than 11% have diabetes. Obesity in your little tract county is less than 0.27. Then you're in this bin here, and this bin has basically the prediction on a regression tree is the average value in the bin. So here your prediction for people with these characteristics is, your prediction for the county area for people with these characteristics is the average is going to be 219. But if we go to an area which has got diabetes greater than 0.01, so that's no, physical inactivity greater than 0.31, greater or equal to 0.31, and non-Hispanic white less than 0.83, so less than 83% Hispanic white, and physical inactivity actually even higher, so greater than 0.33. So you see we've actually branched on this variable twice. Then we have the highest possible categorization, which is 371. And so each time we're just branching on one of these variables until we reach a bin. The bin in classification was a prediction, you know, based on the majority of the classes. If most are ones, we predict one. If most are zeros, we predict zero. But here we just take the average value, and this will be the prediction for, in this case, any county that kind of lands in this bin. And how do regression trees actually work? Well, I put a little bit of information in the notes, but I'll just kind of go over this. So let's just actually take a picture of the screen, and I'll give you a little bit more room. Okay, so let's do a screen snip. And what we do, so we start off with a single node. So here we go. So one, we're going to start with a single node. And then we define, basically for every variable, we find kind of the best split, the split that kind of, so say for health inactivity, we kind of look to see, you know, we'd start off at 0 and go all the way to 1, and which of these values kind of gives us the best split. So define variable splits. For each variable. And then, you know, we find the best, out of all the variables, find the best split. And in this case, this is the split. And again, I have this in more detail in the notes, which gives you the greatest increase in R squared. And so, what's the R squared value here? Well, I'll define that in a minute. But, within this category, the average is 219. There might be a 214. There might be a 216. There might be a 220. There might be a 230. We've got the sum of squared error, which is just going to be each value kind of subtracted from the actual mean prediction here. But I'll define those in a minute. And then we'll basically say, after the split, so the split should increase the R squared, so we should have, a value, closer to all the values in the bin as we split the variables. So after the split, we define our R squared new, and this is for all the data, and what we want to do is we want to see if R squared new is greater or equal to R squared old, and we have 1 plus something called the complexity parameter. And I'll actually write this out here. And again, this is in the notes. So each split should improve the R squared. And again, here, imagine that we had like an average of 250, and we have everything from like we have everything from 210 to 450. As these begin to kind of go out to different nodes, with very similar values, the error gets smaller and smaller and smaller. But what happens is we don't want to make our tree too big. So this functions a little bit like the adjusted R squared in standard regression. It ensures that we have a certain jump in R squared to make the tree bigger. And the whole point of this is, we prevent overfitting. So the whole point is the CP, as we get bigger and bigger and bigger, it's harder and harder and harder to make our trees bigger and bigger. So we actually have to, and what we can do is we can use holdout validation to find the best possible CP. And we'll talk about holdout validation a little bit later. Okay, so on to holdout validation. So holdout validation, again, we've got all these independent variables. So we have all our x's here. And then we have all our items. We have I equals 1, 2, 3, 4, all the way down. We have our x's. And we have our y's, which in this case will actually be a value. So this is going to be in our instance here, this is going to be the rate of heart disease in the zip code. Okay, so sorry, we had a minor graphics card meltdown there. Okay, so where were we? So holdout validation, if you remember exactly as before, we'll say we have tenfold cross-validation or holdout validation. What we will do is we will actually split our data set into 10. And remember, this is where my really bad graphics come in. So we got 1, 2, 3, 4, 5, 6, 7, 8 and 9, it's 10. And if I could draw properly, these would all be of even size. So imagine that we have like 1,000 items in our data set. You know, each of these would have 100 items in. So for each fold, so and if we have 10, it would be like, you know, for I equals 1 to the number of folds, n, what we will do is we would build the model on the remaining and so it would be, so then folds, it would be like so in this case we have 10 folds, basically the 90% of the data, and then we test the model on the remaining data we'd call the holdout data. So in this case it would be the 1 over the number of folds, and in this case it would be 10% of the data. So again, it's very easy visually. I'll just do it for the first item. So the first item, we hold out the green, which is, you know, 1/10. We build the model on the red. And at each stage, we kind of predict. So we make predictions with the models on the holdout data. And we call these like y hat. Okay, so this is very much like regression. So for each item, you know, the error is just going to be yi minus y hat. The only difference here when the holdout thing is we're counting the error on the holdout data. So again, we're building the model on the 9/10, make the predictions with the remaining 1/10, and then we kind of see the difference between the y and the y hat. Now, this should probably tell you that, let's just clear this canvas, there's actually going to be kind of a difference in the errors that we use when we're doing holdout validation with continuous data than with class data. Remember, we had things like precision, recall, specificity, etc. So let's just kind of do a few of these. The first we have is the sum of squared error. So the sum of squared error equals, so imagine that we've gone through the entire process and each item has been in the holdout sample at least once, as we predicted each one. So we've got to predict, we've basically got a holdout prediction for each item. We have each item minus its prediction squared, and we add them all together. Now note that the sum of squared total equals yi minus y bar. And we don't really need the y bar I because it's the mean of all the items squared. This is just like regression. And my r squared is basically 1 minus the sum of squared error all over the sum of squared total. And other things we can use, we can kind of adapt the sum of squared error. We can have some measure of average error. And what we'll do is, to average, we just divide by n, the sum of squared error. And then we're going to take the square root, and this is called the root mean squared error. So it's the mean value of the squared error, and we take the square root of it. And that's standard, and we sometimes compare this with the mean absolute error, which is, and again, I give the full definitions in my notes. And this time we're taking the absolutes. So again, if we're making predictions, so imagine it's a regression, we have to take squares, otherwise everything will kind of cancel each other out. So imagine we have, you know, this sort of situation. We're not perfect fit, but we have, you know, we have some errors. If we didn't do either the absolute or the square, then this would, you know, this would be yi minus y hat would be positive, negative, positive, negative, negative, and things would actually cancel out. So let's just say we had an error of 2, an error of -3, and an error of 4. The mean absolute error would be 1 over 3. Then kind of sum them all together. 2 plus 3 plus 4. That's 7, 9 over 3 equals 3. So that would be my mean absolute error. Okay, so let's kind of go back. Let's go back to how to implement holdout validation in R. So again, it's as we did before. We set up the train control. And this just tells us we're going to do repeated cross-validation. This is the number of folds, and this is how many times we repeat the process. So, you know, we're going to do 10-fold validation, and we're just going to do it once this time. Now, let's actually do it for regression. Yeah, so we see how good regression is as a predictive measure. So we've got our y variable. We have all our independent variables. We have our data set. Method equals lm, which is just R term for regression, and we pass this train control. Okay, so you can see here my R squared is actually a little bit less than it was for the actual regression, and that's probably, you know, because we're using holdout regression. Every time we're testing a prediction, it's based on data we've not built the model on. That's quite nice, actually. We haven't dropped much in R squared when we do the holdout regression. Now let's just do stepwise regression, and here what we do is we actually have our previous stepwise model. We can actually ask for the formula for that model, and this is what the formula the stepwise model gets. Remember, this is the one we did where we removed a lot of the variables, doing a stepwise regression. And now let's do exactly the same. And has it increased? Oh, 680 to 682, 683. So it has got mildly better holdout prediction. We're doing less overfitting. Now let's actually do the decision tree. Now remember, I told you the complexity parameter, the higher the complexity of the parameter, the harder it is to build the tree. It kind of, you know, we need a bigger jump in R squared to kind of split the branches, and we tend to get smaller trees. But conversely, if we make our tree too small, you know, if we just had it the average value, it doesn't have a great deal of predictive power. But if we make our tree too large, it's liable to overfit. So what we're going to do here is we're actually training, and we set exactly the same as before. We set the same train and control, but here we define a parameter called tune grid. And what this does is basically where we use expand.grid. And if you do this yourself, you're just going to have to copy my code. But here, we just kind of give a range of values for the complexity parameter. And the idea is it will actually run this holdout validation for different values of the complexity parameter and find the best value of the complexity parameter. So we're setting it to be this sequence here, which you can see it's going to test all the complexity parameters between 0.0001 and 0.01. And so let's run it. And we can actually plot the holdout. And what it will do is actually it will plot the root mean squared for all my different complexity parameters. So it's literally doing what we did before, but 100 times. And you can see that our best one, you see we go down. We start off here at root mean squared of 39. Then we get better and better and better and better. But then slowly we get worse as our complexity parameter increases and increases. So that's the way of tuning the complexity parameter. Now let's just look back at the holdout. And it actually gives all of this. So it actually gives the values of the r squared and the root mean squared error. And you can see that like the r squared actually increases and then decreases. You notice that the values are still lower than the regression. A simple regression tree doesn't really do much better than, I said it's good at explaining the data, but it generally doesn't give as good of predictions as regression. Okay, so now we're going to do random forests. And again, you can actually do a grid with more than one parameter, but it takes a long time. And this time we're going to use something called MTRY, which is basically, we talked about how we build, random forest is an ensemble method and we build like different trees. MTRY, and each tree has a different number of features. MTRY is actually the number of features we kind of build into each tree. So if we had 5, we build a lot of trees with only 5 random variables. If we have 15, we build all our trees with 15 random variables. Now, I'm going to have to leave you to run this. This actually takes a few hours. And I don't think you want to watch a video just a blank screen for a few hours. But that's just tuning for random forests. Now, the last little set of techniques we're going to use are ridge regression and the lasso. And I'm going to explain this in a little bit more detail. Okay, so I kind of just drew this quickly. Now, a statistical model, it has kind of 2 different properties in terms of performance. It has its bias and it has its variance. You see there. Now, ideally, we want, say we have just have an analogy of a target. This is the result. This is the perfect result. We want low bias and low variance. That's our ideal result. But sometimes it doesn't always work as possible. And we can have high bias. Actually, we're missing the target. We're getting the wrong result. We're kind of consistently wrong here. So, we're maybe consistently estimating our kind of, heart disease rate, maybe wrong by 50 or wrong by 100, but always in the same direction. Or we could have this situation where we have no bias, we're on the right track, but we're very inconsistent. We have a high degree of variance. Now, of course, we could actually get both wrong, and we can be off, and here we are, we're just a bit of a mess. Now, how does this actually relate to statistical models? Okay, so in each of the models we've done, we've got this idea of model complexity. So we have, if you think about, regression, the more independent variables, we're going to be the more complex. And with regression with trees, any sort of tree model, then the more independent variables, kind of in a way, the bigger the tree. So we have our tree, but as our tree gets we have maybe a simple tree here with 2 nodes. We have a more complex tree, and we have an even more complex tree. So as we add more nodes, as we add more decision branches, we get more complex. Okay, so let's think about this in terms of the models now. We have, as models get more and more complex here, now what happens if you had a model that's got no complexity? It's just, for example, it might always kind of give exactly it gives exactly the same prediction, which it's probably not related to anything the model, but say I always predict we have 300 for the heart disease rate, then I'm probably not going to hit. I give the same result every time, so I have low variance, but I'm probably not going to hit the model. I'm probably not going to hit the answer very much, so I have high bias. So up here I have high bias, and as I build my model more and more complex to deal with my data, my bias gets lower and lower and lower. So this is my bias. Okay. Now, what about my actual the variance in my predictions? Well, as my model gets more and more complex, I kind of get more variance because I'm becoming more and more sensitive. If I have a model that's got loads of useless junk predictors and it's been overly kind of fitted on the training set, when I get to the test set, it's liable to have more variance. So kind of my variance goes up. Now we add these two guys together and we get the total error. So there's this kind of trade-off between bias and variance. And we have some kind of optimal model complexity. And this is what we've kind of learned all throughout the class. With the regression model, if I just have one independent variable, it's not going to be very accurate. If I have like everything but the kitchen sink and everything's correlated multicollinear with each other, then again I overfit the data and I don't get predictions. There's kind of all this really means is that there's kind of the perfect model somewhere in the middle. Now, one technique we can do with regression to deal with this bias variance trade-off is what's called regularization. And let's just get back to my black pen. Okay, sorry, video crashed again. So how do we explain regularization? Well, let's just start off. What do we do with regression? So general, what we've been calling OLS, ordinary least squares regression. Okay, well, the answer is we're just trying to minimize the error. So we're trying to minimize basically the sum of the y's minus the error, which is the sum. And let's just say we have k for n items in our data set, and we have like k predictors. We're trying to minimize this guy here. So this is just the regression equation. And this, we kind of hid the math this time, but all we're doing is this is the fitted value here. And all we're trying to do is we're trying to set these betas so that and my y hat gets as close as possible to yi. Now, there's two different types of regularization. The first is ridge regression. Now, let's just call this my OLS equation here. We'll just call this OLS. And with ridge regression, we're going to minimize OLS plus some lambda times, for each of my betas, we're going to minimize the squared beta value. Now, why do we do this? Well, if we sometimes, what we'll do is we'll have large betas which kind of cancel each other out. So if we have two items that are correlated, and this is one of the reasons why multicollinearity is bad, then one might have, so we'll have like, let's just say wages and something like, you know, how much the wages and how much wealth you have. They're going to be pretty correlated. One could be given a really high beta and the other one could be given, say, a really low beta, say really high negative betas. This could be like 100 and this could be minus 100. And these guys are going to cancel each other out. And it might give the perfect solution to the training data set, but we're probably overfitting. So what this does is it basically makes the beta smaller. And the smaller betas, as betas get smaller, so as betas become smaller, then we lose variance. Variance decreases. But if all my betas are 0, then I'm always just going to predict 0, which is going to have very high bias. But bias increases. So if you think here, the high values of lambda, we're trying to minimize this whole thing here. And the high values of lambda just will actually, really relative to the OLS, will kind of drop down the betas. So as lambda increases, this sends the betas to be 0 and the variance decreases and the bias increases. And again, we're going to have some sort of an optional beta that's going to give us our best fit. And the second example is the lasso, spelled lasso, kind of pronounced lasso, not lasso. And this is minimize my OLS plus lambda j equals 0 to k beta j. Now here it's just taking the absolute values. Now this does pretty much the same thing, but the difference is this tends to make betas, some betas hit 0. While ridge regression tends to lower all of the betas more constantly. So what this will do is, say we have, maybe we have something like 1x1 plus 2x2 plus 2.5x3. Ridge regression might actually make one of these to 0 while still keeping these at reasonable amounts. So the lasso might remove this to 0 while still keeping these reasonable amounts. So the lasso is sometimes also used for variable selection. Okay, so that was kind of about as techy as we're going to get in the class, and feel free to email me if you want any more clarification on this. Now let's kind of go back and let's implement and just show you how we can use this stuff practically. Okay, so let's fit the lasso, and we fit it exactly as we did previously. Remember, we fit the tree with parameters, so now we're basically looking and we're trying to find the best value of lambda. So we're trying to find, minimize the error when we do holdout validation, and we're basically trying to find the best lambda. Now, just a few little things. We're using the method called glmnet from the library glmnet, which I actually refer to at the top of the code. And basically, it's got like the parameters. It's got alpha. If you set alpha to 1, it does the lasso. And if you set alpha equals 0, it does ridge regression. And then you've got the lambda parameter, and as I said, the bigger the lambda is, the lower your betas are, and the lower the variance, but the higher the bias. So the idea is you're trying to find the best lambda for the bias variance trade-off. So again, we do exactly that we did before. We do the holdout validation. We're going to use the same train control we had before. And this is beautiful. You can actually see this is my error, my root mean squared error. And as my lambda increases, there we get the minimum error. So my best lambda is around 0.14. And I can actually look at this here, and you can see these are the R squared, and the best R squared is somewhere around 0.14. And you see it starts dropping again. Now let's do the same for ridge regression. And this really doesn't work quite as well. You see these are the R squareds. They're a little bit lower. And let's just look at the plot. And yeah, you can see with as a low value of lambda, you just get the same root mean squared, which is similar to regression. And then it suddenly kind of snakes off. So we can kind of work out this data set that ridge regression, at least ridge regression implemented by our GLMnet, doesn't work very well. So just to summarize, there's lots kind of continuous prediction is very similar to class prediction and holdout validation. You split it into sections. You take most of the data as your training set, and a little bit of that data is, say, a tenth of that data is held out. You build the model in the training set, then you test on the holdout test. You kind of calculate errors, like the root mean squared errors, or you can actually calculate R squared, where R squared is good. And then you can test your parameters. You basically train your method, i.e. you get it as good as possible on the test data sets by testing on a range of the parameters and finding the best value. So, for example, the lasso is the great example. We find what's our optimal lambda, where we run this, and we have our lambda here. So going forward, we're going to actually use that lambda because it's the best lambda. Okay, well, that's it for continuous prediction.